All right, we got chapter 17, rigid body energy and momentum. So here in this first question, we have a flywheel of a small punch that rotates at 300 RPMs. It is known that 800 foot-pounds of work must be done each time a hole is punched. It's asking that the desired speed of the flywheel after one punch be no less than 90% of the original speed of 300 RPMs. So we're being asked to find the moment of inertia, required moment of inertia of the flywheel. And for part B, if a constant 25 pound-foot couple is applied to the shaft of the flywheel, then we're to determine the number of revolutions in which must occur between each punching, knowing that the initial velocity is to be 300 RPMs at the start of each punching. So to kind of start this one out, we take the angular velocities and we convert them to radians per second, so we can easily work with them a little easier. So we have our omega 1 as the 300 RPMs, and we convert that to radians per second, that being 10 pi radians per second, and omega 2 as it being 90% of the 300 RPMs is 9 pi times radians per second. Using the equations, the work and energy equations that we learned in chapters 15 and 16, we're applying them here once again, as the T1 plus U from 1 to 2 is equal to T2. And we know that the work done, or our U value, is the 1,800 foot-pounds. Plugging in this, what we know for our T1 as it being 1/2 times inertia times omega 1 squared, and plugging in our values that we've found for T2, plugging that into a general equation of 1/2 times moment of inertia times 10 pi radians per second squared, squaring that, minus the work done of 1,800 foot-pounds is equal to the 1/2 times moment of inertia times 9 pi radians per second squared. So manipulating the equation, solving for the moment of inertia, we plug in our values, do our simple algebra, and we find that our moment of inertia is 19.2 pounds per foot per second squared. Then for part B, using the integral for the work from 1 to 2 is equal to the integral from theta 1 to theta 2 of the moment times d theta. So plugging in what we know, as theta is representing the number of revolutions that we're trying to find, we plug in our work done at 1,800 foot-pounds is equal to the 25 pound-foot couple times theta. So we find that theta is equal to 72 radians, but then converting that to revolutions, we find that theta is equal to 11.46 revolutions. In this next question, we are given a slender rod that is attached by a pin at one end, so it's free to swing. Initially, it is at rest with respect to the horizontal, and it's then released. So we are being asked to determine the angular velocity of the rod as it passes through a vertical position and determine the corresponding reaction at the pivot. And then for part B, we're asked to solve this expression that we find with the weight of the rod equal to 1.8 pounds and the length equal to 3 feet. So using a similar approach as the first question, using the energy and momentum equations, our velocity equation, r is equal to omega. So here in this first free body diagram, this solid line is at rest and the dashed line is after the rod has been released. As we know, it is being at rest, so any angular velocity or velocity is 0. But as it swings, as it is released, then the weight does then take hold and help and points downward as it passes through vertical, and the velocity is to the left in the x direction, and as it rotates, our omega 2 is clockwise. So to find our v2, we have the v equation, v equals radius times omega, which we can plug in here, which is there. Then we take the kinetic energy of the rod. So we have T2 is equal to 1/2 mv2 squared plus 1/2 I omega 2 squared. Plugging in what we know here as V2 is equal to L over 2 times omega 2 squared. And we have the moment of inertia of a rod is m mass times length squared over 12. So we plug that in there. And converting what we can, we get that T2 is equal to 1/6 times ml squared times omega 2 squared. And we also have the change in potential energy. So the work done from 1 to 2 is equal to the weight times the radius, or L over 2. Continuing, just bringing over things that we've already calculated, as well as a couple of equations. As we know that since we're looking for the angular velocity, we take the derivative of the velocity function that we had. The v2 is equal to L over 2 times omega 2, and we're able to find that in a later section for the reaction. Anyway, so we take this, the T1 plus U from 1 to 2 is equal to T2 equation. We know that T1 is equal to 0, and we plug in our values that we've already calculated for, solving it for omega 2. And we find that omega 2 is equal to 3g over L is equal to the square root of 3g over L in a clockwise direction, as was shown in our free body diagram. Next, to find the reactions, as this was pin connected, we do a similar thing, a similar setup as to what we did in chapter 16. So as we have it vertically, we have the weight going down that is opposite the reaction at point A, or at the pin. We set that equal to the mass times acceleration about the center of the rod. So setting up equilibrium equations, seeing as all the forces are in the y direction, we have our AY, or A, minus the weight is equal to mass times acceleration. And as I was explaining before, we have, since velocity here is equal to 1/2 times L times omega squared, the acceleration is equal to 1/2 times L omega 2 squared. Can I see omega squared? Yeah. No, I just meant just omega 2. 1/2 times L times omega 2 is equal to velocity 2. So then plugging that in, we find that the acceleration is equal to 3g over 2. And then plugging that in for the mass, why do I have an mg there? Oh, that is my fault. Oh, I converted the W to mg. Don't know why, but I did. Because that's not supposed to be there, because that is supposed to then be canceled out, because I forgot to add the mass in there. Yeah, because that's supposed to be mass, so that's our acceleration equation. So we have to also add in the mass there, which then cancels that out, and those cancel. The gravities cancel. Either way, I think I messed up there. So as we plug all these in, we have our A minus the weight is equal to mass times acceleration. Our acceleration is the 3g over 2. As we go through, we have A minus mg is equal to 3gm over 2. Bringing this over, we have 3gm over 2 plus mg over 1. Then doing algebra, giving it a like denominator, we multiply this by 2 over 2, so we have 3 plus 2 mg over 2. And the mg's we can treat as a constant, which is also equal to the weight, so we can pull those out, and then we have 5 over 2 multiplied by the weight in the vertical direction. So that is how we get that expression. So I do apologize for that, mathematical mistake there. So here for part B, we have the weight and the length. So for omega 2, we plug in our length. Also with gravity, as it is in pounds and feet, we use 32.2 feet per second squared. And we find that omega 2 is equal to 5.67 radians per second in the clockwise direction. Excuse me. And then for the reaction at A, we use the 5/2 times W equation. And we find that the vertical component, or the only component at the pin A, is equal to 4.5 pounds in the vertical direction. The next question, we have two identical rods that form a right angle. They are welded together and connected by a pin at point B. We have this spring down here. Is pressed, this assembly, these two rods are pressed up against the spring and released from this position shown. As the max angle of rotation can only be 90 degrees counterclockwise, we are being asked to determine the magnitude of angular velocity of the assembly as it passes through the position where rod AB forms a 30-degree angle with the horizontal. That's kind of a lot, but it's easier as we set it up into 3 different free body diagrams. One being as it is at rest, as it is shown. B2, as it is forming that 30-degree angle with the horizontal. And a third free body diagram as it is completely flipped around, basically mirrored across the rod AB. No, not mirrored, rotated a full basically just as it's shown here. Sorry. So we first want to look at the potential energy here at position 2, so with the 30 degrees. So we have the weight times the height of AB, so from the pin, as we can see that the distances, the lengths are equal. So we have the weight of AB multiplied by HAB in position 2 plus the weight of BC times HBC in position 2. So as H is equal to L over 2, we have the height of AB is L over 2 times sine of 30 times the weight of rod AB plus the weight of rod BC times negative L over 2 times cosine 30, as it would be in the negative y direction for this. And again, we're using a few similar equations from that we learned in chapters 15 and 16. Although I wasn't really sure, I didn't really understand T1 plus V1 is equal to T2 plus V2, but I will look more into that later. But we know that T2 is equal to 1/2 times the moment of inertia about point B times omega 2 squared. And that the moment of inertia about B is equal to 1/3 times the mass of rod AB times the length plus 1/3 times the mass of BC times the length squared. So plugging those in and just doing simple algebra, we find that T2 is equal to 1/6 times the mass of AB plus mass of BC times the length squared times omega 2 squared. And at position 3, as our theta is equal to 90 degrees, we have the velocity, our third velocity, is equal to the weight of BC times L over 2, and T3 is equal to 0. Still not quite sure what the T1 and T2 and T3s are, and so I'll be doing a little more studying and research there so I can understand that more. So now we're continuing on, and we use this conservation of energy equation that I showed previously. But as T1 is equal to 0, it's not quite useful here. So we have T2 plus V2 is equal to T3 plus V3. So we plug in these, what we had calculated on the previous page here. for our T2 here plus V2, just trying to make sure that I have it right. Yeah, so this whole spot is V2, and then T3 is equal to 0, and V3 is the weight of AB times the length over 2. This part took me a minute as I just tried to do the correct algebra to solve for omega 2. And just a whole bunch of calculations and algebra. I got it down to the 3g over 2 times the length times 1 minus sine 30 plus cosine 30. And plugging all of that in, plugging in what we know and calculating it, we get omega 2 is equal to 7.09 radians per second. As that is the angular velocity of the assembly as it passes through the position where rod AB forms a 30-degree angle with the horizontal. The next question, we have something similar to what we've already dealt with in chapter 17, with it being a wheel. This time we have a force couple that is away from the center. We have a bolt that is located 50 millimeters from center of a tire, and applying the couple that is shown, the 100 Newton couple, that's being applied for 0.1 seconds. Wheels initially at rest and free to rotate. We were given that the mass of the wheel is 19 kilograms. The radius of gyration is 250 millimeters. The time, as we know, is equal to 0.1 second. And as we've found from chapter 16, moment of inertia is equal to mk squared. So setting it up just as we did in chapter 16, initially it is at rest, so any angular velocity is 0. We're being asked to determine the resulting angular velocity of the wheel. So just as this couple is being applied. Plus the moment couple times the time that it is being applied is equal to moment of inertia times omega 2, as omega 1 is equal to 0. So in the book it has this set up, the syst momenta 1 plus the impulse from 1 to 2 is equal to system momenta 2. So just kind of figuring that out, maybe helping a little bit there. But as we've done before, we find the moment of inertia as it being 1.1875 kilograms per times meter squared. We use the couple moments equation, m equals fd. We find that the moment is 46 newtons times meters. Then to find the angular velocity, we just set it up just as we did in the free body diagram. Gives us the equation I omega 1 plus mt equal to I omega 2. Plugging in our values and calculating for omega 2, we find that it is equal to 3.87 radians per second. The next question, we have a sphere of radius r and mass m that is projected along a rough horizontal surface with the initial velocity of v naught and angular velocity of omega naught. So if the final velocity of the sphere is to be 0, so meaning A, it comes to rest. We are being asked to find the required magnitude of omega naught in terms of V naught and R, and the time required for the sphere to come to rest in terms of V naught and mu k, this coefficient of kinetic friction. So just as we did in the last question, we set up our free body diagram. So as it is initially moving, plus the contact that it is having with the ground and the frictional force, all of these being multiplied by the time that it's taking, and then as it comes to rest. So here, what we learned in statics, we set it up in an equilibrium equations, as we have all of these unknowns. So just kind of make sense of it, we take our forces in the x direction. So we have mv naught minus force, the frictional force, times time. This is equal to this equation there that we'll be using. The forces in the y, basically normal force plus is equal to the weight, which is just mg. Now if we sum moments about g, we get our third equation. So we have I omega naught minus mv naught times the radius is equal to 0. So solving for omega naught is what we're being asked to for part A. We use equation 3. Plug in our I for a sphere, which is 2/5 times mr squared. And as we manipulate the equation to find omega naught, we get that omega naught is equal to 5 times v naught over 2 times the radius. Now for part B, to find the time, we take our first equation, m v naught is equal to frictional force times time, and substituting the values for the frictional force and manipulating the equation to solve for time, we get that time is equal to v naught over mu k times g. In the next question, we have a circular table with a semicircular panel that raises on hinges. So we're given the radius of the semicircle as radius r, and it's initially held in the vertical direction or vertical position. As the plate and panel are made of the same material, so they have the same thickness, and the entire assembly is free to rotate with initial angular velocity of omega naught as seen in the picture. We're being asked to determine the angular velocity of the assembly after the panel has been released and comes to rest against the plate. Which, honestly, I don't know why we would want to calculate this, but I mean, this is just one of the questions. So here we're given that we have the mass of the circle is equal to m, and mass of the semicircle is m over 2. So first, we look at it when the panel is vertical. So we have 1/2 mr squared. So our moment of inertia 1 is equal to 1/2 mr squared plus 1/4 times the mass of the circular plate times the radius squared. So plugging in the values that we know, I solved this on a separate piece of paper just to save space. So we have our first moment of inertia is equal to 5/8 times mass times m times radius squared. Then when the plate is horizontal, we have our I2 is equal to 1/2 mr squared, so the circular portion, plus the 1/2 times the mass of the semicircle, which is 1/2 times m times radius squared. So solving that, we get that our I2 is equal to 3/4 mr squared. Using conservation of momentum, we set those equal to each other, and we solve for omega 2. Doing simple algebra and manipulating the equation, we get that omega 2 is equal to 5/6 times omega naught. The next question, we have a wooden wheel. Sorry about that. We have a wooden disc that is at rest with a bullet being fired at it, height 1/2 of the radius. As it rests on a horizontal plane, and coefficient of friction between the disc and the plane is finite. So we're being asked to determine the linear velocity v1 and angular velocity omega 1 of the disc immediately after the bullet has penetrated. And then for part B, we're being asked to describe the ensuing motion of the disc and describe its linear velocity after the motion has become uniform. So as we have done before, we set up our free body diagram as it is at rest, so our momenta naught, plus our impulse, the impact, is equal to the system momenta 1. As we did before, equilibrium equations to get our three that do help us. The one equation that kind of confused me was this one, the summing moments about G. I've never really seen it this way, but it does make sense as I worked through the problem with this, just to kind of keeping everything set, I guess. So it was just a little confusing. But once again, as we continue on to find point for part A. So for our initial velocity and omega 1, our v1 and omega 1, the delta t is at 0 seconds, which makes it a lot easier. So as we plug that in, we find that our v1 is equal to mv naught over the mass. So the mass of the bullet times v naught over the mass of the disc. And to find our omega 1, we use this third equation. Again, that r times f delta t goes to 0, as delta t is 0. Is equal to I omega 1. Thus we're left with mv naught equal to r minus h is equal to I omega 1. As the inertia of a disk is equal to 1/2 mr squared. And we plug that in and solve as far as we can until we get it to a good point here of omega 1 is equal to 2 times mv naught over capital M times capital R minus h over r squared. Here then we plug in our value for h as being 1/2 times r. Canceling out what we can, we find that omega 1 is equal to mass of the bullet times v naught over the mass of the disc times the radius. And it is moving in a counterclockwise motion. This is immediately after the bullet has penetrated. Then after the impact and the motion then goes to a uniform motion, we set up a similar free body using what we know, v is equal to r omega. But this time, instead of the I omega going in the counterclockwise direction, it is now rolling in the clockwise direction. So setting this up just as we did before, we have summing moments about point A, so the contact point. So we have mv naught times h plus 0, as all of those get bundled into the sum as they're occurring on that point A, is equal to m, the mass of the disk, times velocity 2 times the radius, plus I omega 2. Continuing on with this equation and plugging in our values, we get that our second velocity is equal to little m v naught over 3 times capital M. And that is occurring in the positive x direction, or to the right. So describing this ensuing motion, so after the impact, so imagine if I'm holding a ball and it gets impacted, it'll slide and it'll rotate back a little bit. And so after something gets hit, it slides and rotates a little bit before catching and then rolling this way. So rolling into a uniform as it should. And so that's just what I've explained here, that the disc slides to the right for a brief moment while rotating counterclockwise, and then later begins to roll with a constant linear and angular velocity, as was shown in the free body diagram. For the last question, we have two gymnasts, one jumping off of a platform that is 2.5 meters tall with respect to point E on the plank. And we have another gymnast at point A and at point C on the beam. And there's a pin or just some type of pivot at point D. So we have the mass of the plank as well as the mass of the two gymnasts. We have the inertia of the plank, the moment of inertia that we're using. There, so we're assuming a perfectly plastic impact, and gymnast A is standing perfectly straight. So we're trying to find the height to which gymnast A will rise. So again, as we have done, we have the three free body diagrams. One as gymnast B is coming down with velocity, plus the instant that both gymnasts are on the plank before gymnast A is launched, and that is equal to our momenta 2. So as gymnast B, this MEVE is now on the plank, and MCVC is equal to the gymnast A with respect to their velocity, multiplied by their velocity, and this HC is the height of gymnast A. And as you can basically assume that the I omega is going to be rotating in the clockwise direction. So setting up equilibrium and plugging in what we know, we have our moment of inertia about point D. We have the 1/3 times mass of the Planck times length squared plus mass of gymnast A times the length squared times omega plus mass of gymnast B or E times length squared times omega. And manipulating the equation to solve for omega, we get our first, or this equation, omega is equal to MEV1 over 1/3 MP plus MC plus ME times L. So first we need to find the velocity of gymnast B. So we use our V is equal to the square root of 2GH to get that. And as we solve for the velocity of gymnast A, so we have a length times omega that we can use from kinematics. We plug in our omega to that same equation and we get our VC is equal to this. And finding the height of gymnast A, we manipulate our first equation, the V equals 2GH, square root of 2GH, for velocity, or for the height, rather. So we have HC is equal to VC squared over 2G. Continuing on with these three equations, we transfer over what we know, and we just start plugging stuff in. So we have our velocity of gymnast B at 7.00357 meters per second. I kept that just for calculation purposes, so I could be as accurate as possible. Plugging that then into our second equation for the velocity of gymnast A is equal to 3.77 meters per second. And then plugging that into the third and final equation to find the height of gymnast A. We take the VC squared over 2 times gravity, and we find that the height of gymnast A is 725 millimeters, or 0.725 meters. So I know that this is lengthy, but thanks.